The Earth has only experienced 5 major ice ages. The first began 2.4 billion years ago when the only life to be found on the planet was ocean-dwelling, unicellular, and anaerobic. This all changed when evolution delivered cyanobacteria, the first organism capable of converting carbon dioxide and water into useful sugars with the help of the sun, photosynthesis. The important difference here, however, was in the waste product generated, gaseous oxygen. Prior to this, the highly reactive gas had never before been found in the atmosphere. Instead, methane, a powerful heat-absorbing greenhouse gas, was found in abundance. The only problem was, in the presence of oxygen, methane reacts to produce carbon dioxide and water vapor. Carbon dioxide, while still a greenhouse gas, isn't nearly as good as methane at retaining heat in the atmosphere, while water vapor mostly would have precipitated out of the air and into the oceans, minimizing its effects on the climate. What this led to was the atmosphere being gradually drained of its methane and replaced by less substantial greenhouse gases, until for the first time ice formed on the surface of the Earth, beginning what's known as the Huronian Ice Age. The extent to which glaciers encompassed the planet during this time is not entirely known, as each subsequent ice age tends to remove nearly all evidence of those preceding it. But we do know that after most of the world had been buried beneath ice for 300 million years, the veil slowly lifted and the Earth transitioned back to a swampy, lush jungle. From here, it was more than 1 billion years before the Earth glazed over with ice once again, this time thought to have been caused by an increase in volcanic activity. Now, considering volcanoes have been, and still are, one of the largest sources of greenhouse gases on our planet, this statement at first might seem backwards. But the other major side effect of volcanism is the creation of new rock on the Earth's surface. And while it's easy to assume that after their formation, these rocks remain mostly fixed and unchanging, this isn't true. Different aspects of the environment are always interacting with one another, either physically or, more importantly to us, chemically. You see, carbon dioxide in the atmosphere can react with water vapor to form carbonic acid. When this weak acid eventually rains down to the surface, it interacts with newly generated rock, like feldspars, leading to what's known as chemical weathering. What this does is alter the feldspar into what's known as kaolinite, while producing calcium and carbonate ions, which, surprise surprise, react to form calcium carbonate, another rock. What this means is that the formation and weathering of new rocks can actually draw carbon dioxide out of the atmosphere and lock it away into new rock. And shortly after, as a result, Earth entered into the most severe glaciation event in history, the Cryogenian Ice Age. Glaciers extended as far as the equator, while the ocean became a mixture of ice sheets and slush, sealing virtually the entire planet beneath a layer of ice. But eventually, either by chance or more likely as a result of the extreme resource limitations of the time, this period saw the evolution of the first predatory zooplankton, which could feast on the virtually defenseless phytoplankton, providing for the first time a control mechanism for these abundant photosynthesizers. So, after 100 million years of sustained volcanism, with oceanic carbon retention at an all-time low, the balance of power shifted back towards greenhouse conditions and the Earth thawed once more. The next ice age wouldn't come for another 200 million years, with what's known as the Andean-Saharan Ice Age. And I have to be honest here, not much is known about this period of glaciation. It's thought to possibly have been the result of a massive collision somewhere in the asteroid belt known as the Ordovician meteor event. What this did was send a large amount of debris into the path of Earth's orbit, which over hundreds of thousands of years would fall to the Earth, increasing the atmospheric dust levels to several orders of magnitude higher than what they are today. And when dust is in the atmosphere, the small particles can sort of act like tiny mirrors, reflecting away sunlight before it can reach the surface, basically the opposite of a greenhouse gas. Whether or not this was the main cause behind the third Ice Age event, we know that only 30 million years were spent under the ice, making this the shortest ice age by far. Not long after this, however, by around 360 million years ago, a new evolutionary path was being explored, which led to another precipitous drop in carbon dioxide and abrupt rise in atmospheric oxygen. For the first time in Earth's history, plants began to grow on land. Before this point, life had essentially been restricted to the oceans, but with the development of things like tree ferns and lycopods, Earth's landmasses were rapidly colonized with carbon dioxide depleting and oxygen producing life. Pretty soon, plants were building structures like lignin and cellulose, which, due to their complex structures, have incredibly slow decomposition rates. This means there was enough time for them to get buried, preventing their further breakdown, and storing the carbon in their bodies beneath the surface into what would eventually become coal. As a result, atmospheric oxygen levels rose to over 35%, while carbon dioxide levels fell below 300 parts per million, and the planet entered the late Paleozoic Ice Age. Ironically, it got so cold that many plants had trouble growing, and oxygen content was so high that fires could burn hotter and larger than they can even now, helping to periodically remove vegetation and return carbon to the atmosphere. On top of this, around 25 million years into this icehouse event, the Earth's many landmasses assembled into a single monolithic continent, Pangaea. With an interior too vast for most moisture to seep in from the oceans, the water that kickstarts chemical weathering wasn't coming in contact with the rocks at the core of the land. As a result of having two major carbon sinks weakened, CO2 could once again begin to build back up in the atmosphere. Just a nudge is all it takes, and from here, as some ice melt began to occur, this revealed the darker surfaces beneath, otherwise known as decreasing the albedo of the planet's surface, leading to greater heat absorption, creating a feedback loop until the Earth was again free from ice. From this point, the Earth had to wait another 200 million years before South America broke apart from Antarctica, opening up the Drake Passage and allowing for the formation of the circumpolar Antarctic Current. What this did was isolate the southern continent from the warmer equatorial currents that otherwise would have been forced to circulate around the pole. Cut off from equatorial heat, Antarctica formed massive ice sheets 41 million years before there would be ice found at the North Pole. But slowly, as the continents continued to break apart, the shoulders of North America and Eurasia closed in around the Arctic Ocean, again blocking those warm equatorial currents from entering the waters here. Meanwhile, the Indian subcontinent was colliding with Asia and as a result was building the Himalayas, or in other words, exposing more rock for the same chemical weathering we talked about earlier, leading to more CO2 leaving the atmosphere and therefore decreasing the world temperatures enough for ice to form at the North Pole, officially marking the start of the Quaternary Ice Age some 2.5 million years ago. Due to the recent timing of this glaciation, this is also the ice age we know by far the most about, and some of the ice created during this glaciation is still on Earth today. By drilling into the ancient ice preserved beneath Antarctica and analyzing the composition of the trapped air bubbles, we've been able to determine historic carbon dioxide levels, dust concentrations, and even reconstruct temperature. Now, looking at this, it's pretty easy to see the correlation between carbon dioxide and temperature, but their correlation with dust might not be as obvious. You see, when the Earth gets colder, the air overall cannot hold as much moisture, and the planet as a whole becomes drier, exposing the surface and allowing for greater amounts of dust to be kicked into the air. So knowing this and going back to this graph, what we can see is that there's a spike in dust particulates every time the Earth's temperature reaches its periodic minimum. But what I really wanted to use this graph to explain was the cycle of colder temperatures followed by relatively warmer ones, all during an overall ice age. These cycles are what's known as glacial interglacial, and it's likely that all previous ice ages experienced similar patterns to these. The cause of this glacial interglacial cycle has to do with the way, or ways, the Earth orbits around the Sun. The Earth's orbit periodically changes in three main ways: precession, obliquity, and eccentricity. Now, correlating any one of these cycles to the glacial interglacial patterns is difficult because they all happen simultaneously, and the effects of one may either cancel out or exaggerate the effects of another. But simply put, we can see that the Earth's relation to the Sun is the source of cyclical changes to the Earth's climate. What this also reveals is that changes in relation to the Sun are not responsible for beginning or ending any of the ice ages. If they were, we'd see ice ages not just behaving but actually occurring cyclically as well. Each one is truly unique. What we can learn from this is that while smaller variations in the Earth's climate can be caused by changes in the Earth's position relative to the Sun, the larger climatic changes, i.e. the ice ages or global warming events, have and always will be determined by the composition of our atmosphere. Using this graph then, we can see that without humans, the Earth would be on track to re-enter a far colder glacial period sometime in the upcoming 50,000 years. But now showing modern carbon dioxide levels, we can see that what we've been putting back into our atmosphere pales in comparison to anything we've seen previously over the past few 100,000 years. And if we've learned anything at this point, it's that because of the Earth's inherent composition, which was determined billions of years ago during its formation, the planet naturally favors greenhouse conditions. Every time the climate has diverged from this, it was in large part due to the removal of greenhouse gases from the atmosphere. And the only way the Earth could return to such conditions was for these gases to be replenished. Today, we're putting this carbon back into the atmosphere and simultaneously reducing the planet's ability to absorb and sequester it. Given enough time, the Earth will react in a huge way to this change for the warmer, which is a problem not because I don't like warm weather, but because humans evolved during and as a result of the icehouse conditions experienced by the Earth historically. These are the ideal conditions for human life, and while the cycles of global warming and cooling have never fully eradicated life on Earth, they have been responsible for mass extinction events nearly every time.